Recording. Okay, so we're very glad to have Tomáš Perutka talking about cones, and I can't remember the exact title.
Yeah, I'll write
Yeah,
it. Right,
great.
So it's the title of the talk is Generalizing Schemes Using Cone Injectivity. This is a paper, so it's a preprint archive which is actually named a little bit different, like that. But I think this is more descriptive for the talk. And fortunately, I have both co-authors here. So it's joined with Tomáš so they can correct me if I say something very stupid, which hopefully doesn't happen very often. Well, so this is in fact a topic from algebraic geometry. This is using category theory to apply it to algebraic geometry, and in fact this is a topic which lies in the very core of algebraic geometry. There's a fundamental notion of it, and for that reason, so let me recall some basic facts about algebraic geometry, which some of you might or might not know. And so I will talk about it a little bit more right now. So what's the goal? What's the goal of algebraic geometry? This is, I think, maybe a stupid question, but quite a fun one. I have, in fact, I will quote David Montfort, one of the famous algebraic geometrists of the last century. And I think this describes it very well. So he said in one of his books that algebraic geometry seems to have acquired the reputation of being esoteric, exclusive, and very abstract, with adherents who are secretly plotting to take over all the rest of mathematics. And he said, in one respect, this last point is accurate. So the goal is take over the whole mathematics. So it's quite ambitious. So how to do that? Well, we can learn. We can inspire a little bit in category theory, which is maybe not that ambitious, but it tries to make an appearance in each branch of mathematics, right? Mostly by going to the area and naming labeling the things with the terminology of category theory. So you can go basically anywhere and say that this is just an lemma or something like that, right? So this might be an inspiration for this. So the basic notion of algebraic geometry nowadays is a scheme. So if we are able to say about many things that they are schemes, this might happen with a little more effort. But in fact, this happened already, because really the algebraic geometry wants to call things schemes and then really use methods from scheme theory to prove non-trivial theorems. This already happened by a very famous proof of Bayes conjectures. So it's not totally made up. It already happened in the proof of Bayes conjectures by Grothendieck, Deligne, and others. And they really entered the field of number theory, which Grothendieck knew nothing about before, and they just started to call things schemes, and then use some cohomology theory applied to schemes, and then really they proved very non-trivial conjectures about number theoretic objects. So this might be not. So this might be really of some use. So the goal is today to make some to try to name things schemes. So if we are able to say about anything that it is a scheme, we might hope to really use very powerful methods of algebraic geometry, which we can use for schemes. So the goal is right now to generalize schemes as much as possible. And in fact, this can be easily done once you generalize some functor called a spectrum. So if you are able to generalize spectra, we are able to generalize schemes. And this is what this talk will be about, how to generalize a spectrum functor. So I will start by...
So by spectrum you mean just the algebraic geometry spectrum?
Yeah. Spectrum of a ring. And I will right now try to recall what the usual situation is. So the usual situation is we have a category of rings. And we have much bigger geometric category of things called local ring spaces. And I will try to local ring spaces. And this is really what a local ring space is. This is a topological space equipped with a sheaf and conditions, which I will talk about later. So really, local ring space is a topological space in which you somehow specify what sort of geometry on this space we are interested in. For example, having sphere, we can have smooth functions on sphere. Then we think about sphere as a smooth manifold. We can have complex functions, holomorphic functions from a sphere, and then we can think of a sphere as a Riemann surface. We can have just for example, continuous function and think about sphere just as over topological space. So this sheaf on this topological space, really, what this does is that it specifies the geometric environment, or it specifies the geometry we are interested in more detail than, for example, topology can do. And so this would be ring spaces. Local ring spaces, this means that there are some conditions which I'm not going to specify right now because it's a little bit technical, but I will come to it later. So okay, so this is the setting. And what we have is a fully faithful functor called spectrum, which goes from rings to, I'm sorry, this should be off. Yeah. It goes from rings up to the local ring spaces, and therefore makes ring into a geometric object. And then you say that the scheme is something which locally looks like a spectrum. This can be easily defined what it means to locally look like something. It's just you have some open cover of space with some inclusion of sheaves. So once you have a spectrum, it's not it's not that hard to define schemes. So you define spectra, and then you say that the schemes are just something locally looking like spectra. So the real issue in generalizing schemes is to generalize this whole situation, right? We have some category we start with, rings. Then we have some spaces modeled by rings, in some sense, local ring spaces. And then we have this spectrum function. And this is really an esoteric object on the first or second or third side, because it's really its definition is really wild. But there is one hope that we can generalize it, because in fact this is this right adjoint to very natural functor. We have the functor gamma going opposite way, which takes this local ring space, so the space and the sheaf, and maps it to global sections of this sheaf. So the value of the sheaf on the biggest open subset of this X. Right, this is a maybe this is a sheaf of rings. This might be good to say this is a sheaf rings. So if we forget all the structure and only thing we remember is the global sections of this sheaf, so this sheaf valued at x, then we get a ring. So this is a function in opposite direction and quite normal one with opposed to the spectrum. So this function of global sections, this is okay. We can think of that quite naturally. And the spectrum is right adjoint. So this is the first observation, that the spectrum is a right adjoint. And this is really the way that helped many people to generalize this whole situation, because once you are able to somehow replace the rings with something, replace local ring spaces with something in such a way that you have this gamma, you can try to come up with this right adjoint. There are really some constructions of spectra. I will hopefully talk about examples a little bit more at the end, but they're all quite involved, so maybe we're not right now. But really there are plenty of them where you kind of guess the construction of the spectrum, and it's always very wild construction. But then, after you get the construction, you prove that it's right adjoint to this, and therefore you know that this is really the notion you are looking for, and you are really able to generalize this whole algebraic geometric situation to the new context. So really the key is into finding well, at first you need to generalize this situation, and then you need to find the right adjoint to this gamma. And what we did, the first thing is existence. In some cases, which I will describe in a minute, there is a setting where this right adjoint exists. We can prove this formally. This is not proved formally in all these situations by now. It's always it's hard work to do this. But we find a way how to do this formally in a large class of cases by just applying algebraic functor theorem in a reasonable way. So there always exists the right adjoint gamma. So what I will try to describe is this situation in which we can do this. A situation in which we can generalize the situation and then prove formally that there exists this right adjoint. So okay, so this is one thing. That really in many situations this spectrum functor exists. This is nice, because you can then use it. But well, if you really want to use it, it's not sufficient to know that it exists, right? You need to somehow construct it, which can be really a bit more difficult than knowing that it exists. So hopefully, fortunately, there is also a second theorem, which is about the construction, and I will really talk about it later in more detail. But we are able once we know that this right adjoint exists, we are able to construct it. I will name it where we are able to construct this function. So not only we know that it exists, but we are able to construct it. And this is really important because then we are really able to work in this situation and hope to apply some algebraic geometric methods to some new environment. Any questions so far or something? Okay. So now I will try to explain all this in more detail. Like what's the generalization, what's the generalization, what are these cases, and what is the construction really. But this might be really of some use because of this theorem there's no need to guess the spectrum function, which is what was done in the past. You somehow guess the spectrum function, then prove that it's right adjoint, and so on and so on. So with this kind of construction, you are able to really do this. So we need to start with replacing the category of rings with something more general. And the thing we replace it with is, in fact, any locally finitely presentable category. You might ask why we need this locally finite representability, and it's mostly because it can be even maybe a bit more general, but we need this is a sufficient condition for the sheaves to behave well. There will be some category, I will call it, let's say A, and we will need to work with A-valued sheaves on a topological spaces, and this is really this enables us to work with them in a way we need. So instead of rings, we can work with a more general kind of category. And next step is really to generalize locally ring spaces. But this is maybe let's start with just ring spaces without the condition on a space and sheaves. This is really a little bit more easy. So we will start with generalizing ring spaces. So this will be, again, we can do it very concretely by really just saying that we have say that we have A-valued sheaves of so the ring space would be topological space and the sheaf of A-valued sheaves. So this is so the sheaf is really some functor from, just to recall what a sheaf is. So this is a functor from open subsets of X up to A. Well, this is just a free sheaf. So what makes it a sheaf is satisfying some descent condition, which maybe there's no need to specify it more concretely. So plus or which enables us to glue things on the open colors. Right. So in order to, okay, so these are objects, and we need to make a whole category. We'll call this category of ringed spaces, which are not ringed spaces but aid spaces. We'll call it aid top. So objects are these. Topological space with a sheaf of A objects. And what are morphisms? So the morphism from X for X, this one aid space, to another one consists of, there is a map of topological spaces, continuous, I'll call it F, and then we have a map, let's call it phi, which goes from the push forward sheaf on, just not to do it wrong. Yeah. Goes from this one, and it kind of wants to go to that one, but this just lives over another space, so I can do something with this OX. This is the goal, but I cannot do that. I can construct a push forward sheaf, which is just defined. This guy is just defined. The value on an open set, let's say U, is just the value of the original on a pre-image of. This is very, very straightforward way to make sheaf here into a sheaf here, right? You just say that value of this new sheaf on open subset of Y is the value of this original sheaf on the pre-image of this. So, okay, so this is the morphism, this pair of things. One morphism of topological spaces, one morphism of sheaves. And in fact, this has a very nice interpretation, which I must say a word about it because it is really nice. We can interpret this A top as a growth and deconstruction. Where we can, I guess most of you know what a growth and deconstruction is, but I will be very brief. So we can do this in the following way. We have a functor which goes from top to cut, and it sends the topological space to the opposite of the category of A-valued sheaves, and having some morphism, then it goes to, okay, I should have more space for this. So this goes to A-valued sheaves on X up. This one goes to A-valued sheaves Y up. And having a continuous map F, this goes to this push forward. Yeah, well, this push forward thing can be made into a functor. So you have a functor push forward pop like this. The push forward is a contravariant functor, so you need B pops here because it takes, for morphism, it takes sheaf. Yeah, it takes sheaf. What am I saying? Yeah, I think it should be okay. So we have a functor which assigns to each topological space this category of sheaves, and the continuous map before functor. And this is a function from top to cut, so we can kind of make growth and reconstruction out of it. And what we get is precisely this, in fact. This is really, you have just there's a space and a sheaf. And the morphisms, it's not hard to think about it, the morphisms need to be defined in this way. So this is, for those who like growth and reconstruction as I do, this might be a nice thing to think about. And let's move on. So we generalize the rings to locally presentable categories, and ring spaces we can define in the very same way. You just don't have a sheaf of rings, but you have a sheaf of objects of A. And now we can finally go to the definition of local ring spaces. Or maybe let me start with a good old case of rings. In fact, so having this as a category of rings, we have the category of locally ring spaces. And in between we have just the category of ring spaces, right? Am I doing it in the wrong direction? Because what am I? No, I did it in the right direction. Sorry. So, well, the thing is that you can define. We have defined this functor global sections going from local ring spaces to rings, but we can define this functor of global sections just going from the ring spaces, right? Because the conditions of a local ring space are not necessary in defining this function. This just takes the ring space and gives us the global sections of it, right? So we can define this function gamma as going from ring spaces without the word locally to rings of, right? And this in fact has very obvious right adjoint, which is the functor which sends a ring R to a local ring space R star, which is just one point, and the value of this, to define the sheaf on one point, you just need to define one ring, and this will be just R. Alright, so you can make ring into this very stupid ring space, which is just one point with R assigned to it. And this is just easily seen to be the right adjoint to this functor gamma. So the interesting thing, in fact, happens here. The interesting thing doesn't happen between rings and ring spaces, but the interesting thing happens because this is very this is really not a local ring space in many cases. So the things really happen. So the interesting stuff really happens here. And the thing is that you have this inclusion. You have this inclusion of local ring spaces into ring spaces. And in fact, the interesting thing is the right adjoint to this inclusion. You can factor this situation through the ring spaces. So there we had gamma going like this, and spectrum going like this. And in fact, we can factor it through ring spaces, and this part is easy. The right adjoint is easily defined as this very stupid looking space. So the interesting stuff happens between inclusion of a local ring space into ring spaces and the right adjoint to that. And this is in fact the thing we constructed in this general case. This really more general thing than just this whole right adjoint, because this is defined for any ring space, not only just for rings. Okay, so to talk about this, I should really right now define local ring spaces in a more generalized environment. So what is so I should probably say what the conditions are. So local ring space is a ring space such that each stalk this is just mean that we are interested in morally this means that we are interested in functions defined near some point, and formally is the colimit for O x u where u are some open neighborhoods of some point x. This is a stalk at a point. Maybe x is an unfortunate letter, so let's use. So for each p, for those who don't know, for each point of x, you can define this co-limit of values of this on an open neighborhoods of p. So this kind of describes some behavior near the point, and this is called stalk. And we want for the ring space to be local ring, we want each stalk to be local ring. And each map between stalks to be local homomorphism. So now, to be very precise, I should define local rings and local homomorphisms, but I won't do that because now is the time to really use category theory and define the general context we have used. Because these conditions are what we are generalizing. These conditions of something to be local ring and something to be local homomorphism. So now let's just jump right into the general case from the case of rings. So we now have so we already generalized the category of rings, and we generalized the definition of ring spaces, and now we need to define local ring spaces in this general context. So we will replace these local rings by something called cone injectivity class, and this is really very similar to injectivity. So, as we know, we say that the object is injective with respect to some class of morphisms. Just recall, right? So we say that x is injective with respect to class of morphism J if for each alpha we have, or maybe let me just draw a picture. So we have this x, we have some morphism which belongs to this J, and we have arbitrary morphism like this. And recall that injectivity of object x means that for any span like this, we are able to find lift or extension, or precise. We are able to find the extension of this morphism along this morphism from this class J. And we can define so this is injectivity of object, and we can define an injectivity of a morphism. So having a morphism F, we say that it's injective with respect to some class J if for any square if it has right lifting property in with respect to this J. So for any square, which with this morphism belonging to J, we have this diagonal lift making both triangles connect. Right? So this is injectivity. So we define a similar thing called cone injectivity, where we don't have a class of morphism, but we have a class of cones. So we have a class of cones. Set cones. And by cones, I really mean that we have not just, in this set there are not, we don't have a set of morphisms, but we have a set of families of morphisms with a same domain. Right? So we have some morphisms. So we have a set of morphisms like this, going from A indexed by two indices, like that. And we say that an object is cone injective with respect to this class. I will call it J once again. J. If. And now for each alpha, for each I and alpha like this, that exists some J such that we have this lift. So this is weaker notion in the sense that if we have the injectivity, then there is really some morphism from J, some morphism like that, and the extension. Right now we have some cone from J, so we have a bunch of morphisms like this. Right? We have a bunch of morphisms like this, some morphism like that. And now we don't need to have extension for each of those, but just for some of them, just for one of them, in fact. So we just for the cone, which is indexed by the J. So for the cone, this is I. So for this cone, we need to find some J, so some domain, such that the extension. It doesn't need to happen for all of them. As opposed to the injectivity. So this is a weaker notion, right? We just have a cone of morphisms, not just separate morphisms, and we just need to calculate it into one of them and not to all of them, right? Is that clear? Okay. So in fact, this can be. I don't think I have time to talk about it, but this can be phrased as the usual injectivity, but not in a category A, but in a free product completion of this category. Because we can somehow freely add products to this category, and then the injectivity, this cone injectivity will be injectivity in this free product completion, but I don't think I had time to talk about it. But it's really nice. So this can be phrased as an injectivity. But let us stick to this definition. And we have defined cone injective objects, and we can also define cone injective morphisms as just having the right lifting property, right or left, right lifting property with respect to with respect to the members of the cones. So we say the morphism is called injective. And now this will be the same as here. For each cone, for each square, where here we have some morphism appearing in some of the cones. Here is some morphism in some of the cones. And here we have some other morphisms. So for each of these squares, we have the diagonal filler, making these triangles. So this is just the good old right-lifting property. Now we don't need to do the same thing we do here. Like there exists some index such that this factor is there. No. This is just the usual right-lifting property with respect to all these morphisms appearing in subcode. So yeah, so this is the cone injectivity of objects and of morphisms. And why is this useful here? Well, in fact, the local rings are just cone injected objects in a category of rings with some cone looking like this.
Sorry, I just missed the definition. So you want for every ij a map into. So for every ij you want a square.
Yeah.
It's only for one square.
This is really just right-lifting property for the set of morphisms aij. Okay, and in a case we are starting with, we have the cone like this. We have a ring with 2 free elements, which satisfies the fact that their addition is 1, and then we invert one of them, either the first one or the second one. So this is just the free ring with 2 elements which add to 1, and this is the free ring these are the free rings which one of them is invertible. And this is a cone, right? And the cone injectivity with respect to this gives us local rings. Local ring is a ring with unique maximal ideal. And it's not entirely obvious that this really gives us local rings, but it's a known thing that it's equivalent to being local. And local homomorphisms, so cone injective morphisms with respect to this cone, will be just morphisms such that they reflect being unit. The image, or I can phrase it like in the following way, that it maps the unique maximal ideal into the unique maximal ideal of the targeted thing. So
maybe you can say just like by definition of cone injectivity with respect to this morphism, it says that if you have a ring and 2 elements that add to 1, then one of them is invertible. Is that it?
Yeah.
And that's equivalent to this maximal ideal.
To having all non-unit elements in one ideal. Right. So and this cone injectivity is the condition we have on the stalks in the definition of local rings. We want the stalks to be local rings and mapped between stalks to be local homomorphisms, and so this can be generalized to cone injectivity. So
So being a local homomorphism means reflecting invertibility?
Yeah.
Is that right? Yeah.
Exactly. So now we generalized ring spaces, and now we are going to generalize local ring spaces through this injectivity, cone injectivity process. So, another definition. So we have A, locally finitely representable category, and we have a J, a set of cones. Okay. And we have a B, non-full subcategory of cone-injective objects and cone-injective morphisms. So we find B to be subcategory of cone-injective objects and morphisms with respect to this collection of cones, J. So now, let's define the generalization of local ring spaces, and let's call it A, B, top. Like that. These are ring spaces. This is just the full subcategory. This is just a subcategory of this A top, the generalization of ring spaces, with some condition. So here. Objects. This is the full subcategory of a top with objects these are just these spaces with each stalk being cone injected. Point. So belonging to this category of to this subcategory B of cone injected morphism. And morphisms. This is some X, this is some, what is it? The pair of a continuous map and a map of sheaves. So F by such that this induces a map on stalks for each point. We have a by the definition of the stalk is a code image. This induces a map. Let's call it FP from the stalk and the image of that. To the stalk with so the stalk P. And this should be cone injective morphism. So this also should belong to the category B. Right, so now local ring spaces are subcategory of or this generalization of local ring spaces is the subcategory of A top consisting of those spaces with stalks and map between them being cone injected. And this is really the generalization we are looking for. And the theorem now is, so the theorem can be now phrased correctly. The inclusion of these A, B spaces into A spaces has right adjoint. I will call it spec with not capital S because it's going from all these A spaces and not just from A. So it has this right adjoint spec, small spec. And this is really a non-trivial step because once again, this gamma, this function of global section gamma going from A sub to A has right adjoint, trivially defined by this one point space. This is the same as with rings. So this is really where the hard work is being done. And the proof is well, it's not that easy as I write it, but it's just the application of adjoint functor theorem. But well, each step, each part of the adjoint functor theorem is not really obvious right now, because you can at first you need to prove that this inclusion respects colimits, which in order to do that you need to actually define what the you need to actually figure out that this has colimits and how they look like, and then you need to prove that this inclusion respects them, and it's not entirely obvious. It's in fact quite not obvious. And then you need to verify the solution set condition, and to verify the solution set condition, you really need to use small object argument which is adapted to this code injectivity. Like for the normal injectivity, you have some sort of small object argument, and you can somehow adapt it to this cone injectivity. So by that you in fact in the end by the small object argument for cone injectivity you get the solution set condition you need in adjoint functor theorem. And then with some hard work you can just happily apply adjoint functor theorem and you obtain this right adjoint. But yeah, so this is the one part, and the other part is the construction. So I will just say how the construction look like, because it's maybe a little bit surprising knowing the key case of rings. I mean, in the usual construction of spectrum, the points of the space are primes. The topology on the space is very wild, and it's not even Hauser or something. And the sheaf is also very indirectly defined, and it's all a mess. But this kind of maybe explains some stuff. For example, how prime ideals just pop out. And so let me briefly say something about it. So define now big spec R, and this is now the object of A, right? And so we can just apply both of these constructions. You can make it into a ring space by making it one point space with this as a global section, and then you can apply this found right adjoint. And so this is this small spec applied to this one point ring space, right? This is the composition of those two functions. And point, at first what point looks like. Point of this space corresponds bijectively to localizations. I would say what it is. Localization in this context is something which we use in the small G argument. So this is something obtained from the maps in cones by taking transfinite compositions of push-outs of coproduct. Right. So this is just the trans, or something having right lifting property to this co-injected map. Maybe it's right.
I'll say both at the same time. So it's a map which is a configuration to a finite object.
Yeah. So something having. So the localization, we can say that it is just something having left lifting property with respect to co-injected maps. And we want this to have cone-injective codomain. So it's localizations going from R to cone-injective. In fact, there's a little bit stronger statement that the category R over B, this is equivalent to the category R over B being having connected components corresponding to these maps. So these are points. In the case of rings, maybe let me here. So in a case of rings, these maps corresponds to homomorphisms from R to some ring which is R localized at the prime ideal. So these maps, in the case of rings, these maps in fact corresponds to prime ideals, but what's really going on is this cone injectivity. So it's really about local rings and not about prime ideals. They just pop out because of this correspondence. So it's a little bit maybe surprising that it's not that about prime ideals, but it's more about local things. And
can I ask one question there? Just in the definition of localization, there was two formulations. One is a sort of cellular map that is like a transfinite composite of coproducts of pushouts, and the other as via the left lifting property. And the cellular maps always have the left lifting property, but the converse isn't always true. So in this setting, if you have the left lifting property, is it automatically the case that it's a transfinite composite of?
Maybe I get it wrong.
I'll say this cellular closure. But
yeah, okay.
It's a more cellular, maybe.
Okay. So yeah, this might be right. I'm sorry. So it's called cellular.
Maybe you have to check the director.
Maybe maybe if that might be true. But.
Yeah, but in the case of rings, this just corresponds to these maps to localization with respect to prime ideals. And open subsets corresponds to finite localizations, which are maps which we just get by a finite amount of coproducts and pushouts from the map in code. And in case of rings, these are just localizations which inverts an element. Let's go to A. So these corresponds to, so these open subsets in a case of a spectrum of the ring corresponds to elements and inverting them. And in this general case, this is generalized to finite localizations. And for the structure sheet, which is maybe the hardest part, we have a the idea is that on these open subsets, so for each of these open subsets, we have a pre-sheaf defined on these open subsets. One of them corresponds to some finite localization, and we can send this finite localization to its codomain. This is a pre-sheaf on these open subsets, and we can then can extend it to all open subsets, and then sheafify. And this, in fact, gives us what we want. So I will not talk about it in more detail. Even here, the description is not quite obvious. On some open sets which are not these. And yeah, so we can construct this thing in this general setting like this. So everything is really about this cone injectivity and this say cellular maps with cone injective codomains. These correspond to points of this spectrum. And just very briefly to mention some examples, just to know that it's not completely useless. So from what's known, there are like 3 examples which we came up with. One of them is, of course, the basic one, the rings. The other one is monoids. So you not work with sheaves of rings, but just with sheaves of monoids. And the cone is just identity and inclusion of natural numbers into integers. This is the cone, and cone injective objects are all monoids, of course. That's this. So everything needs to be cone injected. And the morphisms once again reflect invertibility. And these spaces are used in the theory of, they are used in something called F1 geometry, which is very mysterious part of geometry, which kind of tries to adapt the proof of Bayes conjectures done by Grothendieck and Berlin to the proof of Riemann hypothesis. But it's really right now the state of art is just to try some optimal notion of F1 scheme. And one proposed notion of F1 scheme is really this locally ringed space defined via this cone injectivity with respect to this cone. So these are so what we get are some F1 schemes in sense of Dijkmar and Kato and others, I believe. And the other example are smooth rings or C-infinity rings. This is the category we start with, and these are rings with many operations, not just addition and multiplication. In fact, these are rings which have defined for each smooth function from Rn to Rm, we have one operation. So there's like infinitely many operations. So in fact, these are algebras for Levere theory, which is modeled by a category of where objects are just Rn and morphisms are smooth functions. So it might seem like a little bit wild structure, but for each manifold, the smooth functions from it to the real numbers form a smooth ring. So these C-infinity rings, I will not talk about it in more detail, but we have again some code looking like the one for rings, and we have some notion of a local C-infinity ring. And the schemes, so we can again form a spectrum via this construction, And the schemes we get by this are called C-infinity schemes. And they include manifolds. Smooth manifolds. So smooth manifolds are schemes in this context of C-infinity rings. By the way, these are also used in forming models for synthetic differential geometry. These C-infinity rings. So it's really something quite nice. And I believe there are more examples, but we are working on them right now. So there's also this formal spectrum, but I should really not talk about it right now. I should really stop here. So yeah, that's it. Thank you.
Thanks very much. So, does anyone have any questions? Go ahead.
Yeah, so maybe a fourth example. There's already a functor which is called Spec, which goes from the diffusibility lattices to spectral spaces. So that can be an example with because the localizations then are just the two-element Boolean algebras. So if you take A to be the category of diffusibility lattices and B to be the singleton category, which is just the two-element Boolean algebra, then probably you will get like this.
I believe that there are some examples in the spirit of what you say. I've tried to read something about it, but I really in this we really focused on the geometric side. But yeah, there are some more of a logical nature examples. Yeah, that's true. That's true.
Julio.
Yeah. You said we wanted to sort of obtain some similar notion to the classical one, and then use some theoretical machinery. Does that really generalize to this new concept?
So yeah, you can so having the spectrum, you can define schemes, because you can say that a scheme is something which locally looks like a spectrum. That's easy. And of course, then the hard work is to try to use some scheme theory to actually prove some theorems. And I don't know what's the state of art exactly in this F1 geometry. I think there are people working on it, right? In these contexts, but I guess I don't have a concrete example of some theorem proved in these two cases. But in the case of a formal spectrum, which I believe is also example, but I'm not really done with proving it. We just generalize this to some sort of topological rings instead of rings. So in that context, the theory of formal schemes is established, and there are many applications of it.
So you don't get the old school form.
You cannot apply just everything formal. No. You really need to figure out how to use these methods in this context.
Any more? Yeah.
Yeah, just in the theorem too. So in the abstract theorem, right? You said the point corresponds to localization, which in some sense, I think of Plymouth replacement of R, right? So you have a cellular map into a conjective object, some conjective object, right? And in your example of rings, it's not just some local ring; it's a localization of the ring R. Is it easy to see that every local ring together with the cellular map is actually localization of R and not of some other ring? Right?
So if you look at the cellular map, then finite compositions of push-out.
Yeah.
So you have this very concrete, cone, of course.
Yeah.
And the push-out. So if you look at the push-out, what it does, it adds to a ring an inverse to a single element. Okay. And then if you do transfinite composition, you get a general a map from a ring to another ring where you invert some of the elements. Okay. And then if it's also co-injective, then it's a local ring.
And they're unique up to equivalence or something like that. So these co-injective objects together with the cellular map. Are they So you say they're unique of isomorphism? Because I mean, you give me a way to construct a conjective object together with a cellular map, but if I have some other, does it have to arise in this way?
Yes, that's the nature of cellular maps. If you have some concentration as a transfinite composition of push-outs, that's somehow that tells you which elements you invert. And then so it's always like that. So you invert some set of elements.
All right.
That also, of course, corresponds to saying that in this small object argument for coding injectivity, it doesn't produce a single thing, but many things. We have many localizations.
Any more questions? Have you looked at the relationship with the work of Yves Deers and these people who do stuff about cones and spectra a bit?
Yeah, so we are currently trying to look at something. Well, the thing is, yeah, so the Beers approach is a little bit different because he use multi-adjoints instead of these. But this notion is in fact very similar because multi-adjoint is just a functor which happens to be adjoint between the product completion. So yeah, it's quite, yeah, some of the ideas are quite similar. Interesting, yeah. Well, for example, the Beers has also some other examples than these ones using some logical constructions and stuff like that. But really, I haven't seen these geometric applications in this work of Beers, like the F1 schemes and stuff like that. Yeah. Well, but we're trying to figure out the more connection between.
Okay. If there's any questions online, feel free to ask one. Or if not, then I thank Tomáš again for a great talk. And so next week we have Henrik Winter talking about some stuff from geometry of a algebraic flavor, but yeah, so that's next week, and so see you then. So